everybody, I'm Skowronek, and I'll be talking to you about the techniques that we're using when we're reverse engineering mobile devices for our product at Corellium. But really, the focus is going to be on how we built the Linux for M1, the first one that worked, and on the techniques themselves that you can apply on QEMU or any simulator you like, and maybe even build your own like we did. So first, a few words about myself. I actually came to reverse engineering via a different path than many of you, I imagine. It didn't go through security research, but instead I actually trained as an electronic engineer. I used to be a GPU designer, then I built security hardware, and this is kind of where this really started getting interesting for me. And over the time, I've also built a large portfolio of hobby projects, you know, Linux for Octane, PSP breaks, Linux for the iPhone, and my own motherboard, which, you know, was very exciting. But one thing that I noticed that they all had in common is that they included a fairly hefty dose of reverse engineering. Because a lot of vendors don't really think about interoperating their hardware with anybody else's. For instance, if you're going with Intel, you're going to get an Intel blob to operate their CPU's memory training. And I actually wanted to do something novel in that and use one of the memory channels for my own purpose. And of course, I had to reverse engineer that. And this has been kind of a pattern that to get interoperability between the different components I wanted to use, I had to reverse engineer stuff. And you know, over 20 years of doing that, I kind of have developed a very intuitive methodology that is largely based on runtime observation. It's dynamic, as opposed to just, you know, sitting in IDA, which we also do, but, you know, that's the last resort. But today I'm going to focus on what we did for the Apple CPUs. This is, of course, what my company, Corellium, is most famous for. We started fairly early, 3 years ago, and our first look was at the A8. The A8, which is found in the iPhone 6, is a fairly conventional mobile SoC. You know, you have your 2 ARM cores. You have your GPU on the left, which is labeled SGX. You have a number of display blocks and video processing blocks on top, and you have your external interfaces at the bottom. And none of that was really non-standard. Of course, Apple put their twist on everything because they like designing their own IP. This chip did have some licensed components. The GPU and the video decompression block were Imagination technologies, which helped us a lot. And the USB is a Synopsys product. So we got a bit of a start on those. And of course, it's normal ARM architecture at the time, pretty standard, and it made it fairly approachable. But you know, as time passed, Apple started customizing their chips and extending them. And you can see the evolutionary path that they traced on the next few slides. And you will see that there's 2 main themes. First one, Apple is coming up with new stuff and adding their own IP to the product. And the second one is that there's more and more and more programmable blocks. So Apple loves coprocessors. For instance, in the A9, iPhone 6s, they have introduced the always-on processor, the AOP, which manages tasks like audio output, you know, like switches, sensors, and a few other details. In a way, it replaced an external piece of hardware, the sensor hub that was present in the previous phone. Then in A10, Apple came up with a new design for their cores. They were still ARM compatible, although a newer version. It was ARM v8.1 with, well, privilege access never. And then they also made a few changes. They added yet another coprocessor, the power management processor. They have replaced the built-in coprocessor that managed NAND flash, the Apple NAND subsystem, with an external NVMe flash, which I think may have been the first use of NVMe in a mobile device. And instead, they came up with a very clever way of managing the memory accesses from the thing, about which I'll be telling you later, the SART. Well, SART and NVMe IOMMU. Then in A11, Apple really hit their stride. The A11 is a blueprint for all current products that they have. They have significantly improved the performance of the fast cores. They have added 4 little cores, which are actually still pretty fast. They have renewed the display block completely. So, for us, this means we had to reverse engineer it again. And they have also built their own video decoder. They have significantly enhanced the GPU. The Apple NAND subsystem is back. They moved the NVMe, part of the NVMe management on chip. And they, of course, have moved the secure enclave to 64-bit. But you can still see that it's very much an evolutionary path. So the reason why I'm presenting this is that you can see that it was very easy for us to get started on the A8, and the incremental changes, such as adding the pointer authentication to all of the important processing cores, so the main cores and the secure enclave, in A12, was really an incremental change for us as well, just like it was for Apple. Then in A13, they have added the special PPL mode, which I think generally the community calls not sideways. Well, the extra, basically, privilege levels that they have on the side. And the neural engine, which we really haven't looked into too much. And then in A14, you can see the growing complexity by how I had to scale the image to fit. They have renewed the cores again, adding the AMX, of which I'll be dropping a bit of info. Audio DMA, the display control processor, yet another coprocessor, and just general speedups. And finally, we get to the M1. The M1 is kind of a sibling of the A14, and the major differences between them, as far as our reverse engineering effort goes, is that they have more processors. They have 2 more fast cores than any of their previous chips. And they have the converged I/O block. Converged I/O means Thunderbolt and USB 4, which I'll briefly cover because I think it's of significant interest to those of you that want to look for vulnerabilities. So what do we really do? Is the first step to our reverse engineering effort is to make a register-level model of as much hardware as we can get information on without looking into the source code, without looking into the decompiled code. Because this is a lot of effort. It's a lot easier to just start out with like a stub model. I went too further. And then the next step is to validate your model. Because it's very easy to come up with a plausible sequence of events that should have happened without actually confirming it when you're doing reverse engineering. You have an idea that, for instance, this register causes this action, but how do you really check? So you have 2 ways. You can either run the original software on your model, and of course that's what we normally do. But every now and then we get the opportunity to do the validation the other way around, where we write our own software and run it on the real hardware. So with Apple, this is notoriously difficult. They have lockdown bootloaders that will generally not permit you to load your own software. And our first chance to really try this different way of validation was when Checkrin came out 2 years ago. This was a breakthrough which allowed us to write our own operating system kernel for the iPhone 7. And we kind of developed it into a Linux port that you could actually load on your cell phone and run it. And it was a very good validation platform for us. But something that happened last year really transformed this approach for us, which was that the sibling of the newest iPhone SoC showed up in laptops and Mac Minis, and those traditionally have a way to unlock their bootloaders. So you can imagine that the day Apple released the unlock bootloader version, the developer beta of macOS 12, I ran out to Best Buy and came back with a Mac Mini. And that's basically where our work immediately started on making the model for it. So how do you get started on that? Well, there's actually quite a lot of public information about the structure of those chips. First, there's a completely unencrypted and readily decodable device tree. Every package of firmware contains one of those. In case of the M1, there's for 3 platforms, the MacBook Pro, and the Mac Mini. And the device tree will enumerate every single block inside the chip. So, we take this and we basically build this stub model. And the essence of the stub model is to cover every range that the device, memory range that the device tree describes, and have something in it that will just log an access. And this sounds obvious, but there's something that you really want to do when you do that. You want to log the whole backtrace that you can get from that access, and you want to log a thread ID. We use a shortened thread ID. It's basically a hash of one of the system registers in the CPU that holds the pointer to the thread base. Because with those two pieces of information, you can reconstruct not only the actual accesses that happen, but also exactly what code did it. So you can spot a pattern in the access list, and then take the addresses in there, figure out if they are related, because they'll be on the same thread ID, and then look it up in your favorite disassembler. Well, IDA in this case. So you can see that, for instance, on the top right, you have an MMIO read from a register inside the UART range. This is literally the first access that XNU on M1 will do. And then it is satisfied with what it read, apparently, because it executes a write of OX44, so capital D, standing for Darwin. That's the first thing that prints out. Oh, look, we found the serial port, and we know which register is going to be the status register, the read, and the output register, the write. And you know, by basically following this simple, intuitive approach, you can save yourself quite a lot of reading of this assembly. And here's a more complicated example, because they kind of all build on each other, right? Like once you have certainty about how one thing works, you can use it as a building block, and I'll show that in the next 2 slides. So here's the piece of hardware that pretty much every single block that can send events to the CPU will contain, a little IRQ subcontroller. And this controller contains 2 memory elements, a mask and a status bit. And of course, the event that comes in from the left will set the status bit, and an acknowledge will clear it. And this pattern, you know, then the events get masked, and you have the mask status, which is sometimes available, and then you have the common IRQ line that actually interrupts the CPU that goes to the main interrupt controller. And understanding that this is a very common hardware design pattern means that you don't necessarily have to really get into details of the disassembly, because you know that there will be a few registers. There will be the status, the mask, or enable, the acknowledge, and optionally a mask status. And then you basically, on the bottom right, you have a sequence of accesses that show how those registers can be identified instantly. First, there is the acknowledge of the root interrupt controller, the AIC. The AIC is fortunately documented in the public open source Apple sources, so we don't have to reverse engineer that one. But then you can see that immediately after getting an interrupt, the operating system proceeds to read a register. And then it immediately writes the same value it read into the same register. Well, that's an acknowledge sequence. You don't even have to look anywhere else. And then you take the register address that you got from it, and you look what nearby registers were set with things that look like bit masks during the peripheral initialization process. Well, that's going to be your enable, or mask, depending whether it's active high or active low. And in this way, I have successfully reverse engineered a lot of peripherals, up to the housekeeping point without actually having to even look at the disassembly. The next more interesting part is all of those coprocessors that I mentioned that Apple loves so much. And all of them have a very similar structure. You will have the main CPU, the processor. It will be an ARM core, because Apple really likes ARM. It could be a Cortex-M for small peripherals, or it could be a Cortex-A for older chips, or their own cores for the newer chips. But fundamentally, they all fulfill the same function. They run a bit of firmware, which is usually based on something called RTKit. And then they communicate with the host CPU via 2 mailboxes, an inbox and an outbox. I drew them as queues. I believe they're actually a single item. It's not critical how you model them for any purpose, as long as you obey the status bits. And you can see that the mailbox exchange is pretty simple. First, the CPU gets started by setting the run bit in the control register. You can see that bit 4 got set. Then we send an IRQ, which is not shown here, just I started the IRQ line, and we watch what it's gonna do. Well, it always reads a status bit first when it gets an IRQ, and so it does. And then after reading a status bit, if it's satisfied, here you probably want to glance at this assembly and see what bit gets checked. But when it's satisfied, it's going to read a value from the mailbox, which for newer Apple CPUs and the bigger coprocessors is 128-bit. And then it will respond by performing a write. And so it does a write and reads another status register. And here you again look at this assembly thanks to the backtrace that you dump. And this is basically how you know how to talk to a coprocessor. And they all look more or less like that, even though the addresses will differ between specific processors in the chip. Now, we have figured out the lowest level, the MMIO level of the coprocessor. But because Apple tends to have very regular and clean designs, as I mentioned, they all use the same RTKit runtime in their coprocessors. They have basically followed exactly the same designs for all of them, except the secure enclave on the modern CPUs. And so the coprocessor contains a number of endpoints. Usually it's countable on 2 hands, except for the AOP, which has like tens. Follows the same exact process for discovering those endpoints. And then it has the same request-response conventions where you will send an tagged request. Well, it always sends an tagged request and a reply with the same tag and possibly a bit set to signal that it's a reply. And here you have an example of such an exchange. So at first, the processor boots. And so you can see that we send out a message containing the version on the endpoint 0. Right? EP0 is RT-body, which is the operating system side that communicates with the RTKit runtime. And so we say that we are version 11.11. And then the CPU receives that message from the mailbox and evaluates whether it likes this version. Fortunately, if it doesn't, it'll tell you what it wants with a panic message, so you can correct your model. And so it will reply with the same version, saying that, yeah, I'm also this version. Then you have to send in an endpoint list. And this endpoint list, comes in modern versions of iOS and in macOS and the M1, will come in multiple parts. 32 endpoints are enumerated per message. So you have a little bit masks for endpoint 0, and I declare endpoint 0 to 7. Those are all management kind of built-in RTKit endpoints. And then you reply with another message saying, well, I also support endpoint 32, and by the way, that's it. The high bit set tells XNU that this is the last endpoint being enumerated. 32 is usually the endpoint that most of the real action, the stuff that you actually want to model, will be happening over. But to get there, you have to do all of this anyway. So how do you figure out what endpoints are there? Well, you use the IOReg tool. If you run IOReg on a live Mac, you're going to get, for every of those coprocessors, a list of endpoints that it has with names, which really helps out figure out what you're supposed to do. The RT-body protocol occasionally changes, but it's generally quite stable. I think we had one major revision since iOS 11. And then, of course, you dump the traffic like I dumped it on the right side, and you see what it responds when you send it messages. Sometimes it's a panic. That's usually the most informative thing it can show. Now, a bit more about those fixed endpoints, because this is actually something that will save you a lot of time if you want to mess with this. There's the management endpoint that you already saw in action. And then there's a few system ones. My personal favorite is the crash log. So the crash log endpoint, if you give it a memory address to write the crash logs to, will actually give you very detailed information on what the coprocessor thinks you did to it. It's like a panic, but a lot more detailed. So it will have a list of threads, a text message, of course. It will have a backtrace inside the coprocessor. It'll have a list of all messages you exchanged with it, so you can validate if your mailbox reverse engineering went well. And then it sometimes has a lot of extra text information. I really snipped it because that was pages and pages of NVMe information. You even get details on the flash. So this happened when I screwed up sending a command to NVMe. I got this wonderful report. Well, I said we were sending an address of the crash log. It's not just an address. Apple has been really leading the charge in putting IOMMUs on every single block capable of DMA. In iPhone 6, the IOMMUs were really used for two things: preventing external access from PCI Express to memory, which was not fully successful. There were some bugs in that. I believe that people managed to get into the iPhone 7 via that path. And the second thing is they were linearizing their video memory, so it could be displayed by the display engine as a single stretch of virtual memory. Today, Apple has really gotten the IOMMU religion. They call them DARTs, I think DMA address translation table or whatever, remap table. And they are everywhere. And for security exploitation, this is somewhat hindering, because they will prevent you, even if you take control of one of those numerous coprocessors, you will not be able to just scribble over kernel memory willy-nilly. But for us, reverse engineers that just want to make things work together when they were not intended to, they are a godsend. Because one of the things that have always been very difficult for me doing reverse engineering is figuring out how DMA works. But if you can dump the page table from the IOMMU, it basically tells you exactly where you should be writing or reading from. It gives you a complete map of the virtual space. This one even tells you what other MMIO the coprocessor is likely to access. Addresses that start with 08 are physical memory on Apple platforms. Addresses that start 02 are MMIO. There's some high MMIO that is used for PCI Express. But this is basically free information that you didn't have to work very hard for. And to me, this is really key to being efficient at reverse engineering hardware. So as I said, Apple has gotten the IOMMU region. They have 24 of them now, and the GPU has its own. And the NVMe has a little special one that I'll be talking about in the next slide. No, next then. So another place where you really want to have the ability to dump page tables was unexpectedly, at least to us, the device memory types. So the ARM architecture is uncommonly fine-grained at what it lets you specify about memory. On x86, you have the memory type range registers, MTRRs, that you can use to say to the CPU that some memory should be, cached or write-back policy. But on ARM, you can actually say much more about device memory, too. It's not just, oh, I sent an MMIO. You can, for instance, request that the target device responds to you with an acknowledge, or you can, for instance, say that there cannot be any reordering of memory requests going to the device, and so on and so on. And there's two types that are used the most, NG and R and E, which is the most restrictive. You cannot reorder, you cannot send a new request before the previous one completes, and so on and so on and so on. And the second one is NG and RE, which allows you to send requests to write without having to acknowledge them. So Linux, of course, uses NG and RE because it's faster by default. And we were wondering, why the hell are all of our register writes just going nowhere and having no effect when we were bringing up Linux on M1? Well, as it turns out, for them to actually work, you have to issue them with the more restrictive memory access type. And then, about 2 weeks later, when we were working on PCI Express, we had the same exact problem, which felt very odd. As it turns out, for PCI Express, you have to request no write acknowledge, because otherwise your writes get black-holed as well. So this actually was quite a find, and the only reason we could really figure out how it worked is because we have a model, we ran the XNU kernel inside the model, and we dump the page table, and you can see that the ranges that correspond to PCI Express are posted write and GNRE, and the ranges that correspond to unchip MMIO have the more restrictive policy. So you can see that this is basically something that we'd probably be stuck trying random things for quite a long time before we figured out what to do. And having a model made it into a one-day affair. And it was 1 day because we didn't even know we should look for it, because this is a very unusual feature. So I promised I would give you a little bit of information on AMX. So AMX is a vector extension. It's a shared unit used by the cores inside the M1 or the A14, or I think A13 may have had it. It's actually a really powerful and very cleverly designed vector processor. So, you know, I used to work on GPUs, which were probably the largest vector processors made after the demise of Cray. I guess Next still makes some. And the way we did it, we were very restrictive about how the vectors have to be aligned in registers. So Apple actually did something really cute there, and they permit the vector to start within a vector register and continue and then wrap to the next register in a ring. And this is really brilliant if you're doing things like audio processing, which is what they use it for instance, in A14. But figuring it out wasn't really obvious unless you can run the software and see what it's doing and compare the results between your model and real hardware. Because, you know, it's not going to segfault because you get it wrong. It's just numbers. The audio is not going to sound right, but what is right anyway? Plus, how do you evaluate it automatically? But thanks to having a model, you could actually just compare it. We did our reverse engineering before M1 was on the market as part of our iPhone 12 models. And it was kind of really fun to do. We got started by noticing a very characteristic sequence in FFTs. If you want more information, however, we're going to do a talk about that a while ago. But there's been an open effort on this by Douglas Johnson. If you Google for it, there's some very good detail in there. And we kind of felt it would be very redundant to get into more on that. So this is really about, like, use a model. It will save you so much time. Just trying to figure it out from this assembly would be hellish, because the instruction encodings don't actually contain the whole instruction. Some of it is passed as data from a register, and that is usually generated on the fly by the Accelerate framework. And here there's this little detail that shows basically that even in something that is ostensibly standard, like NVMe, you know, you can just download a specification for it, Apple manages to surprise us once more. So, as I have mentioned, Apple tries to have an IOMMU in front of every device that can do DMA. And there is a significant overhead in managing an IOMMU. You have to allocate virtual memory ranges, you have to create the mappings, you have to flash the tables after you're done doing that, especially after Unmap. So some designers at Apple clearly noticed that they can do better than that, and they came up with a little sideband IOMMU exclusively for NVMe. And only for the data transfers, too. So when you talk to an NVMe flash device, you send requests that contain a tag, and it responds with the same tag. So you already have to have allocated tags. You can declare in NVMe spec a maximum size for a request, for instance, 256 kilobytes. So they looked at it, and they thought, well, we already allocate tags. Let's use the tag as part of the virtual address. And then within that tag, it's going to be a simple linear access from 0 to whatever the maximum size of the request is. So this is how the special NVMe IOMMU works. And this showed up in iPhone 7 and was one of the reasons why we had to do pretty unspeakable things to the Linux kernel to get NVMe to work on that platform. Because it also uses that classic Dart IOMMU for non-data accesses. And in A14 and M1, Apple surprised us again by introducing what they call linear submission queues, which is not standard NVMe again. It's somewhat more efficient if you only support one queue. It simplifies your design quite a bit. So this is another reason why we had to stick our fingers into the NVMe driver in Linux. You know, their platform is very custom, even if they have some standard components. And finally, I would like to give you a very short overview of the really innovative feature that Apple added in the M1. It's USB 4. So USB 4, despite being called USB, has very little in common with the USB that you all love to exploit. So there's no, they have basically borrowed the whole design from Thunderbolt. And I don't know if you have familiarity with Thunderbolt. I mean, it started out at Intel called Lightpeak. It's a high-speed serial bus that can tunnel other protocols inside it. It also has a native mode, but I haven't seen that used a ton. And the really cool thing about it is that it gives you external PCI Express or USB, and you have those basically very easy way of doing this breakout, and you can daisy chain it. So Thunderbolt, unlike USB, which is this hub and spoke structure, Thunderbolt is based on a network of routers that even has a protocol for resolution of loops that allows you to connect peripherals to the host, but also hosts to each other, possibly through a bunch of peripherals. It's extremely flexible. And so USB 4 is basically this with a somewhat updated physical layer as far as I care. And it is really cool to see the Thunderbolt technology making it into a standard, because I'm really hoping it's going to take off. The flexibility of being able to tunnel PCI Express is worth it by itself. The good news is that just before, well, short time before our Linux on M1 port, the USB Implementers Forum released the first version of the USB 4 spec. So at least we didn't have to reverse engineer the higher level protocols. Intel has in fact contributed support for USB 4 to the Linux kernel, where there was some initial Thunderbolt work that actually went pretty far by Andreas Never. But of course, you know, this is Apple, so it's not going to be completely compatible. It's not just a matter of loading the Intel driver. So, of course, what they changed was the host interface. And this is why Linux on M1 actually cuts the Linux Thunderbolt stack in half and allows you to substitute your own host interface drivers. They moved it to MMIO instead of PCI Express based. This is basically a ring-based interface. Thunderbolt has very neat layers that carried over to USB 4. You do not have to understand the higher level protocols such as router discovery to get your own NHI driver working. The way they do it is every element in the system has a register space. You know, like USB, classic USB has descriptors and has feature flags that you can set or clear and some control messages that people can customize. Well, Thunderbolt and USB 4 have register spaces. They are fairly complex. They allow you to discover the individual subspaces at runtime. And most of the spaces are fairly well defined. But as it turns out, you know, upon closer inspection, both Intel and Apple have their customized register spaces because there is space for vendor extensions. And everybody uses vendor extensions. So yes, the incompatible NHI was the first thing. Then we needed to boot a Cortex-M3 coprocessor to even get it working. To boot the Cortex-M3 coprocessor, you had to unlock a clock, which is different from all other clocks for some reason. It's like this magic sequence of things you have to do. And to unlock that clock, you have to have the physical layer running. Most physical layers for high-speed protocols have two functions. First one is actually talking to the wire and receiving and sending the messages. But the second function is that they also provide clocks to whatever talks to them. Some physical layers will have an elastic buffer where the clocks get decoupled, but many of them actually clock some hardware. And that's what we ran into here. You cannot start Thunderbolt higher level functions without getting the PHY completely operational. So this PHY is shared between USB 3, you know, super speed, between USB 4, Thunderbolt, and between the DisplayPort output. And so we had to basically figure out how to switch it between those different modes and so on and so on. And all of this was, of course, done by observing MMIO writes and trying to find common patterns. Well, the final result was that you can generally run GAN Linux on at least some versions of the M1. I think that the best bet is to basically see if you can start, you know, any native code on it, and if you can, then it'll probably work. This is a native port. There's some misconceptions floating around that we are using a hypervisor to provide a translation layer or something like this. This is not true. We ran directly on the physical hardware. We have a little preloader, but its role is really limited to translating Apple device trees to Linux device trees. Because the device tree on Apple isn't static. When iBoot loads you, it patches the device tree in a number of places with information such as the tunables that allow high-speed physical layers to actually work. And so we had to carry this over into Linux so we could do the same thing. The preloader is open source, of course. just like everything else in this project. After that, I'm just gonna give you a very short overview of surprises we had with the peripherals. Really old MacBooks use pretty standard Intel-style keyboard and mouse. Well, the last generation of x86 MacBooks already moved those to SPI bus, and they use a custom protocol. Fortunately, that didn't change to the M1 laptops, so keyboard and mouse do work. The touch bar is quite complex. There's a separate display controller just for the touch bar. So I guess technically you could treat it as a frame buffer. Apropos display controllers, this is something that I've seen people wonder about on Twitter. And I have to dash some hopes, because the hopes that I've seen expressed were that by using this display coprocessor, Apple has basically stabilized and regularized the protocol to talk to the display controller. Well, actually, it changes every single version. It's a major maintenance effort for us. Every time they issue a new version, the protocol is different, has different, even the same messages just have different ID numbers. Bluetooth is mostly standard. It's HCI, but they wrapped it into a PCI Express ring protocol. So if you want to get Bluetooth working, you'll basically have to deal with PCI Express rings to submit the messages instead of a serial port. And this was kind of sad for us, because we were kind of hoping to use the Mac Mini as a validation and test platform for a hypervisor product. But it doesn't support GPUs, as far as we can tell. We were really hoping to demo that, but we couldn't get either AMD or NVIDIA GPUs to work, because the memory types that the PCI controller supports are not compatible. This was, by the way, the big reason why we were working on Thunderbolt. And the second thing is the hypervisor is not fully compliant with the ARM specification. It only supports one of the modes that Linux needs. But it's still a very nice little machine. I have one running as a server at home. It's pretty much no trouble. So, I just wanted to give you an overview what we had to do for the Apple hardware, show that the company that sets out to design its own hardware has so much freedom if they don't, just buy IP blocks from somebody else, that it'll keep us reverse engineers busy for the next decades. And I wanted to give you an overview of the techniques and emphasize the importance of using dynamic tools for reverse engineering. Because I very often see people just sitting in front of IDA, and this is a way to do it. It's just a very painful way for me personally. So I wanted to share some approaches you can use to avoid that. Thank you very much for attending my talk. I hope that some of you will, stick your fingers into one of the many open source projects aiming to model hardware. For instance, QEMU for iOS. There's an open source project that does it. And see what you can do.